All right, good afternoon and welcome to the 2:30 session for Donner Doom 2016. My name is Kevin O'Shea. I'll be your host for the afternoon here, and it is my pleasure to introduce Karthik Ramani. Karthik Ramani is a professor in the School of Mechanical Engineering here at Purdue University. He earned his B.Tech from the Indian Institute of Technology, Madras, in 1985, an MS from Ohio State University in 1987, and a Ph.D. from Stanford University in 1991. All in mechanical engineering. He has published over 200 peer-reviewed papers, over 90 journal publications, over 70 invited presentations, and granted 10 patents. Major areas of emphasis in his research are computer support for early design, shape searching, sketch-based design, cyber and design learning, sustainable design, and natural user interfaces for shape modeling. Today, he will present a talk titled, Computer as Partner, It is All Within the Reach of Our Hands. Now, please silence all of your electronic devices, but don't put them away. We hope to see you tweeting to the hashtag DonnerDoom, and posting to Facebook, Snapchat, Instagram, and whatever other social media you want to use. Join me in welcoming Dr. Karthik Ramani.
Thank you, and I'm happy to be here presenting all my students' work and everyone else that works in our lab. So my topic for today is computer as a partner, and as you might guess, it's not that robots are going to take over the world. So you might have guessed I'm more of an optimist, and I don't believe in the doom part of Dawn or Doom. And then clearly, I'm not going to talk about issues related to the doom part, but basically, I strongly believe that the current bilateral trade and interdependence between various entities reduce the probability of conflict first. And second, that there are a lot of organizations like United Nations, World Bank, WTO, NATO, and so on, that are all there for mediation. Nuclear weapons position is itself a deterrent. Nobody wants to kill everybody. And all these things kind of put the doom side of things to rest. And of course, a lot of these things get magnified today. You have a robbery down across Cranard here, and very soon the parents of the kids somewhere else in the world hear about it, and they're calling to find out what's going on. And they think Purdue is full of all crime going on, which is really not true. So I think the media and information and so on have magnified the doom side. So with that, I'm going to be talking about computers as a partner. And just to give you a quick snapshot of some history, it's worthwhile to look at how computers were, how we think they are, and how we think they're going to be, and what can they be in the future? So I want to talk about it. But first, the ENIACs, 1946, right? The way we interacted with computers was with plugs, literally, using our hands. And they were bigger than rooms. Roughly speaking, I kind of have 100x there. What it means is that I'm just wanting to compare the relative speed of computing and computers and look at their implications as we move forward. And then there were the UNIVACs, roughly about 1 million x, which means that for the same amount of energy, it did 1 million more calculations per energy. But roughly think about it as a unit measure that computing and computers, in the way that they did calculations in the past, mostly they did calculations. In fact, the ENIAC was mostly used for artillery and ballistic research by the Army, and they thought it was a giant brain, right? And then the first time we really started interacting with computers in some way of using our eyes was the PDP-11. And the first game was written on computers. A two-person game was written by Stuart Russell. And at that time, they were barely able to do square root calculations to kind of simulate gravity, right? And then we have the Cray, supercomputer, billion times that. In fact, today's iPads are more powerful than the Cray. Isn't that surprising? And after that, we sort of moved to what I call the laptop era, sort of, a laptop in 2009, and roughly 1 trillion times computing power in a relative scale. But with all this computer power, right, what does it mean, right? I just want you to understand what this computer power really means. And just to sort of give you a feel for exponential growth, it's hard to understand what this exponential growth can do to us and to interaction of computers with humans. I want to sort of illustrate this with a story, and let's just grasp the idea of computer power better. So it's a story of an Indian king that used to play chess, and he was a chess enthusiast, and so he called, he used to have visitors around, and he called one of the wise visitors up there, and he always liked to challenge them. And to motivate, he offered any reward to them. And there was a sage that came by and he said, what I want if I win is grains, and just put a grain in the first square of the chessboard, and 2 in the second, 4 in the third, 8 in next one, 16, 32, and so on and so forth, right? And so, of course, the king lost, and he thought this is a humble, modest person, and so let's give him rewards, and brought a few sacks of grain, and they started working on this. And pretty soon, he realized that this was too huge, too humongous, and by the time you get to the 64th square, it's 2 power 63, and it boils down to so many rice grains. And of course, he couldn't afford it. But more importantly, if you stack up all these rice grains, you kind of go from Earth to the nearest star and back. So that's a huge, huge, huge number, right? So if computer power is also kind of doubling, like Moore's law, in the same manner, what's going to happen, right? But that's not the key part of the story. In spite of increasing the computer power, one of the things that I want to emphasize that we haven't done well is figure out how we as humans can use them well. For instance, just for picking up this clicker and using it, I didn't need a manual or something like that. I just picked it up and looked at the arrows, and there you go, I'm clicking on it, right? So, well, there was a guy called Doug Engelbart at Xerox PARC, and also at Stanford. In fact, I had met him when I started there. And it turns out he created the first mouse, right? 1963. But the patent for the first mouse didn't realize itself in terms of a commercial product until 1985, because people simply couldn't make the mouse precise enough and fast enough for the mass scale, right? But basically, we still are living in the mouse era. The mice is not dead yet. It's well and alive. But also, at the same time, what happened subsequently was this idea of a WIMP system came up. WIMP means windows, icons, menus, and pointers, right? Still big and alive, and pretty much drives a lot of our interfaces. And the mouse and the WIMP sort of characterize how most of us work today. Computer, keyboard, that's work, right? So the story doesn't end there, right? The size of computers or chips that can compute have also continuously become smaller and smaller and smaller. Just to give you a feel for that, well, in terms of reduction in size in chips, in 1972, assume the chip was the size of a Volkswagen there, right? What is the size of the chip now? How much would it have shrunk to? Well, it would have shrunk to the size of an iPod, right? Not even 5 iPods, perhaps less than an iPod. But basically, that's where we are. And the point here is that, well, computers are powerful. Computers have become smaller and smaller. Well, computers don't have to look like computers. We still haven't taken something off here to make stuff happen for humans. So what's that thing that we haven't worked on and that is so challenging for us to take the next steps? So I call this the friction between the man and the machine, right? So this is a hard problem, right? How can we make computers become more intuitive and easier to use? Just like I said, I pick up something and I'm using it, and I learned it from living in the real world. And so we're going to spend much of our time on understanding how and in what ways can we think about computers themselves, number one, and the shape of them, and how can we make our interactions with the so-called new computers faster, easier, better, so that we don't even have to think about it. It just happens, right? So in this new world, what we are challenged with is designing these new intuitive interfaces. And I would go to the extent of saying that we want to design interfaces that don't exist. And I'll change that story towards the end. But computers have to use our senses. How do we interact with computers? Well, visual, right? That's why Google is trying to create Google Glass. They don't want you to use a mouse and a screen. They want to put the information right into our eyes, right? Or we can hear from them. We can use our hands. We can use tools. We are very good at using tools. And we can use tools to interact with stuff, right? And then the spatial part of it. We live in a physical world. We move our body, right? We call these our kinesthetic senses. And a lot of our learning today actually, in fact, always has happened by using our hands and body, right? It's not that our hands and body are disconnected from our brain. So we call this embodied interfaces, meaning that the hand is an extension to our body. And then the learning sciences are rediscovering that is indeed true. So where are we? So how are we transitioning? So what I want to talk a little bit about is how are we transitioning from the so-called UI, well, the user interface, to the so-called natural user interfaces, which is sort of emerging. So let's think a little bit about it. So how did we interact with computers? Like after the screen came in, well, we had to type instructions to it. In fact, you had to even know these instructions, so much so that very few people could really compute, right? And then they were very strict and very codified, right? So it was very hard to really do stuff with computers. And then there were the GUIs, or the graphical user interfaces. This kind of made things a lot easier. In fact, all of us live in the GUI world mostly. And the GUIs made all the interaction metaphors better, and people could explore more. You could switch between things. And with the mouse, if you were around when the mouse became commercial, late 80s, 90s, et cetera, you'll sort of remember the time when Macintosh came in and they put it all in place. But after that, what have we done, right? What were the new forms of interaction that really started changing things? Well, we all know. It was the tablets and the iPhones. And this, we can think of this as the first emergence of the so-called natural user interface. So what does it mean, right? It means a kid can pick it up and they can learn it just by using their fingers. They don't even need pens, right? So your fingers are a mode of interaction with it, and it's direct, it's intuitive. Well, not so intuitive maybe, but more direct and intuitive than the previous predecessors. So I kind of want to talk about this idea of natural and the idea of making use of our senses that we have lived with, we have learned, we have worked with. And so what does that mean, right? So, well, the world we have lived in so far, I would say, has taken our extensive capabilities as humans, our intuition, our hypothesis generation, our creativity, all the things that we do that computers can't yet do, right? Of course, you're having computer vision, driving cars, starting to do that, but they are very specific forms of learned intelligence, and I'll come to that towards the end of my talk. But basically what we have done is taken our brain and smashed it into a tablet, and we are sort of really, really imprisoned in this world. That's where we are right now, and we have plenty of room to continue to grow in this area. In fact, I think this is going to be what is going to redefine the next century, is our interaction with computers. And you can already start seeing that happen with things like autonomous cars and so on. Okay, so what about NUIs? Now that you know what these NUIs are, we'll talk a little bit about it. So the tablets, right? And as I mentioned, the tablets has a microphone, has a speaker, and they are as powerful as a Cray computer of 1985. Has GPS, receiver, accelerometer, gyroscopes, has all of that stuff. But the important thing to note is all of those stuff have become digital. And they become small, and they can be put on this tablet, right? And they're getting even smaller. And then the screens have become high definition and so on, and this costs less than $500. Right? So clearly we are in the beginning of a very, very broad shift that is starting to occur, and of course you can make tablets with it. But an interesting thing started happening recently, and we started working with things like this before things like this came to the commercial world. So that kind of is why I'm here giving the talk. Otherwise, we wouldn't be doing all this cool stuff that we are doing, and people wouldn't give us funding to do all the cool stuff we are doing. So these Kinects and Xbox was the first, I would say, extensively used commercial depth sensor. It was the fastest selling electronic device at some point. It uses our body to interact with the computers. And what's going on now, they're getting smaller and smaller and smaller. They've gone digital, of course, and the software for that is starting to get better. And they're going to be in your phones, okay? Already Google's, their new tablets already have depth sensors in it. So you're not going to be living in the camera world, but living in a world that is going to take pictures in 3D and so on. Your FaceTime is going to be in 3D, and things that you do are going to be in 3D, right? So that's the world we were born in, we want to live in. And then there was this thing called Oculus, actually came from one of my colleagues and friends' labs in USC that puts you in a world called the virtual reality world. Basically, these are completely synthesized worlds, and you just live in that world. You don't see the real world. And then there's the beginning of what we call the augmented reality. And if you really want to know what's going on here, there's a new company called Magic Leap that Google has invested $2 billion, and Jack Ma of Alibaba has put $800 million. They still don't have a product out there yet, but you can kind of see this whale coming out of a basketball court. And that's what it's going to be like. You can go to Google, you can view it. We kind of know these kind of technologies that are coming. We play with them all the time. But what's going to happen is already in place. What's going to happen in the next 5 years is already in place in startups, okay? So here, the difference between AR and VR is here you're going to see the real world, which means you can be walking and talking, but you're going to see an embedded physical world on top of this virtual world, okay? And that makes a huge difference. Why? Because the growth potential of this is going to be several times the growth potential of this. That's very, very important to happen. But here, at the center of all of it is we are still going to try to make the humans happen. And here's a Minority Report. Everybody has seen it. So, we had seen it too. And about 9 years ago, when we started seeing the potential of depth sensors to change a lot of paradigms for research, we started saying, well, we should try to figure out how we can make the hands do stuff. And so I'm going to talk about 3 things, okay? My first part is how can we make robotics very simple and very intuitive, but you have to be able to create robots. I'll also talk about that and show you how you can make robots. Kids can make robots that are simple and easy to make and easy to control and so on. Second part is going to be about taking everyday objects that you find and making them interactive, but also we'll see how you can make the space around things that we have more interactive, right? So we'll make objects interactive. And then I'm going to talk about how we can make our hands as a part of a UI, right? Our user interface, not on a computer, but it's now shifting to our hands. So how do we think about that? So those are the 3 things I'm going to talk about. All right, so let's get on our first topic, right? Making robotics intuitive and approachable. Well, robotics is scary for most people. Well, maybe not, but it's hard for you to just go into a room one fine day and say, I'm going to make a robot. I wanted to do this and I wanted to do that. Well, can we do that, right? So that's what we are going to see. I'm going to have one of our lab's maker students bring out one of those in a minute and show you how it's going to look. But let's see what we have to do before you make a robot. You have to make a robot come alive. And how do you make it come alive? Let's say that you have a soft toy, or you just have a bunch of objects you stick together and make some kind of a shape, and you want to make a robot out of it. It's still sitting in the screen, right? We want to make it come out of the screen, become real, and do stuff. How difficult can that be, right? So we're going to talk a little bit about it. And so our first intuition towards doing that was, let's first make the robot look like a robot, come out of the screen. So here's a simple Kinect scanner. You can take the soft toy and scan it. It'll create a whole bunch of points, and you can mesh it, and they're all triangles that make the shape, and then you have a nice model of the small dino, okay? And now we want to make it. So we'll talk about how this is going to happen. So I'm just going to give you an overview of this. So you scan the stuff, and then we'll have the computer do all the stuff that is stuff for the human. So a very important idea is like computers do what they are good at, right? And we impose our intuition on top of our computers, what we know well. So we know where its legs are, where its tails are, and so on. So we can help it figure that out. And then we want it to move. So we start putting motions on top of those features that we want to put motion on. And then we want to make it. So we'll make the computer figure those things out that are hard to us, and it's just doing all these calculations in the back. It's figuring out all the things that are going to take you a lot of time to figure out and has been figured out by others, so you don't have to. So you just use that, and then we'll make a robot out of it. Well, this robot is not a robot yet. It's just out of cardboard or metal and so on. So I'm going to show you a little bit of how the making process works, and soon after that, we'll start seeing how we can work with this. So notice that the manufacturing process plan and everything is sort of happening for you, and the user is pretty much broken it up to pieces, and out comes all the parts, right? So then you can assemble it. Of course, you can do it for any kind of shape that you wanted to transform. So where are we on this? We are testing it on a lot of children right now. We want to make this piece become very intuitive, and making complex things easy and all this computational power accessible to children is pretty hard. I can tell you that. If it doesn't work, they'll tell you it doesn't work. So kind of moving here, so a lot of things are happening on the back. Just to give you a feel for what's going on, a lot of the optimization of how to find these contours, where to cut it, how to make it straight. And then you saw a resolution button, where you could change the complexity of what you want to make. Just with the slider bar, you could control how complex the leg is going to be. So you're kind of playing around with the shape, how good or how fine details you want to capture, as well as fabrication time. So we made all those very simple as a slider. And also, it turns out that you can create a lot of objects on the computer which can't be made, right? So making sure that this can be made, any object you make here in our algorithm should be manufacturable. It's pretty hard because you have to learn so many things in courses like design for manufacturing and so on. We kind of embedded all those ideas on the backside, and it's actually optimizing and figuring out that it doesn't self-intersect. And in fact, you can cut it out of a flat sheet of cardboard or metal and so on and fold it. Okay. So, and then you kind of also saw all these cool widgets that help you put the axes and turn it, and then it generates a whole kit for you, right? The whole kit and all the hinges and how do you put it together. All that is sort of happening on the backside. And then we are sort of getting ready here. Well, so now how do you make it come alive, right? So that's the next challenge. So as you can see, right, well, in general robotics, why is everybody not making robots, right? There's so much of talk about it. Only few people can do it, right? It's sort of, we are in the state of technology where we have all these electronics which is getting cheaper and widely available. You can write all kinds of code. Well, only perhaps some people can write all kinds of code. And then you have all these laser cutters, 3D printers, water jet machines, and so on. All these things are all digital now, right? So that convergence, all are getting digital. But yet, making robots is still hard. Well, not so. We are going to show you a new type of robot, or new types of robots. And it's a spin-off from our lab called Zero UI. And Zero UI is doing this, meaning I talked about NUI, natural user interfaces. We are now, well, talking about no user interfaces. So we'll have our Hyzo. So our new robot is just starting to make its way here. That's Zyro. It's one of our robots, and it's waving its hands. So Dio is controlling it. So Dio, how long did you take to make that robot?
This one took about maybe 15 minutes to make. Not long, 15 to 20 minutes.
Just 15 minutes?
Yeah, 15 minutes is enough for you to put together one robot like this.
And how long did it take to transform Zyro to Rover?
Oh, that would take probably about 5 minutes, because with the same modules that we use here, we can just take this apart, we can just remove them and convert into something else, like a rover like that.
So what does it mean to me as a parent then?
Well, it's good as a parent because you don't need to just keep buying new toys. This is a toy or a kit that you can just get one, and then it's going to evolve according to the age of the child. So as long as the child grows up, the toy also grows up with it, because they can just build new and new toys as long as the imagination.
That's pretty cool. So how do you program these robots?
It's pretty simple. You just have an app, and because this is one thing that we want to bring people out of their tablets, so having zero user interface. So just use an app to program it once, and after you program it, you're basically done. You can just put your phone apart and just play with it for as long as you want. Until you have another idea to make another robot.
So apps sound too complex to program. So what does the app do?
The app is fully visual, so you don't need to know any type of programming language. You basically have to just be able to see it, and you're gonna look at it. You're gonna configure it the way you want it, and after that, you just put your phone away.
Okay, I see. So the app just maps your hand to the robot. So meaning that if you wiggle your fingers and if you want the arm to move, that's just a tap of a button.
Exactly.
And then if you want the robot to turn, when you move your hands to the left or to the right, or if you want it to work like a car, go in front or go backwards, just like an accelerator pedal, all those are just taps on the app?
Exactly. Those are just taps. You basically just get your app. It's fully visual, as I said. You just choose what kind of gesture you want to do to control your robot, everything fully visual, and it's going to be working for you. It's pretty simple, very intuitive.
So it takes maybe 4 or 5 minutes to map your hands to the robot?
Maybe even less.
Less than that.
Less than 5 minutes.
Cool. All right, that's cool. So thanks, Gio.
Sure.
I'm going to show you a quick video of Zero UI's robot here. And most of the actors you see are students that are all now employed by the startup that spun off from the School of Mechanical Engineering.
That's me. That's Spencer. this is our office. The Zero UI team gave us a few robotics kits to mess around with. Ever since I was a kid, I wanted a simpler, more natural interface with my creations. These are the guys from Zero UI. Their dream is to make robotics easy and fun for everyone. Their team created the Zyro, the world's first hand gesture controlled robotics kit for everyone. Zyro consists of 3 parts: the motorized modules, the smart glove, and the smartphone app. Zyro's modular design enables free-form robotics construction, enabling you to build virtually anything. Modules can be animated in a hinge or 360-degree rotational movement. Pair your glove to the modules with the smartphone app and bring your robot to life. Whether you're a robotics enthusiast, an aspiring superhero, evil genius in training, or someone looking to expand their creativity, Zyro is for you. Zyro is for all ages and all genders. There's no limitations. You can design and build it from scratch or use a pre-made starter kit. Design, build, rebuild. Zyro can be used over and over again, making new and different robots each time with the same modules. Learning should be fun and engaging. Unleash your creativity and be at the forefront of robotic technology with Zyro. Zyro.
Okay, so we have been working a lot with children, and we do summer workshops with them and so on. And this is a great way to get them not only engaged, but then they're going to ask questions. You can see this bunch of curious kids in the Indianapolis Children's Museum. And then they want to learn programming. And then, once you get it with your hands, you can go start playing with code and so on. And of course, we got a lot of publicity after the CES show, and went quite viral. And also, this was something that we dreamt that we were, Zero UI was, and the robot was also named to be Lego's worst nightmare, because you don't need those Lego blocks to make these robots. You produce 49 billion of those plastic blocks, and it's so very sustainable as well. Okay, so we're going to move to the second part very quickly. So I'm going to talk about how you can take a kitchen table and make it very interactive. Take everyday objects and make it your controller for things around you, your TV or whatever. And then I'll show you a little bit about how you can take the space around a phone and make that become a place where you can build and make things. Okay, so this is one of our early projects down in 2011-12 timeframe, part of a PhD student's dissertation. And what you're seeing here is a table, a regular table, but he's drawing on the table and working on the table with his hands. It's detecting all his hands, all his fingers, pretty much like what you do in an iPad, but we were able to demonstrate here up to 10 hands, all the fingers, left and right hand, and so on and so forth. So we were the first to be able to show such large-scale interaction on any surface. And sort of just to give you a feel for what's going on, when the depth camera looks in, the algorithms are breaking up the volume over the surface into different zones and interactively fitting a hand model on top and tracking all the hands real time. So we were able to do that. And next, we sort of started wondering, well, phone is still a 2D screen, right? How can we use the power of the phone, the computing power of the phone, but around it, can we make the space around the phone become interactive? And so we designed a smart pen with sensors and made use of the ability for detecting the pen with the phone's magnet. But the pen is also smart in the sense that it understands the gestures, how you're holding it, and so on. So we started working with this type of mobile input and the positions and orientations of the pen and so on. We wanted to figure it out sort of real time and make it do things that would be interesting for us to do as people. So the space behind the pen becomes the active zone and above. But also we were designing interactions which are discrete, like buttons and so on, or continuous interactions like you're drawing things and or having a slider bar. You have a lot of controllers in the real world which are like sliding controllers. So the spatial zoning and tracking, we worked on those things. So I'll show you a little bit of what we could do here. So what you're seeing on the left is as humans, we think that you don't want a second world when you're computing. You don't want to go into the computer world to compute. We want the technology to blend the real world with the computer world. So you kind of see that theme coming again and again, the merging of the physical world with the computing world, trying to design things intuitively and make them come out in the physical world, and also be able to control them intuitively. So what you're seeing here is actually the pen taking a virtual object, and the phone understands where the physical object's coordinate systems are, and you're actually assembling onto it. So that character really doesn't exist there, right? So that's the kind of things you can do. So you're kind of seeing the input modalities at play. And then what you can also do here is using the spatial capabilities of the pen, you can zone in on certain regions. You can put sounds into that bird. So next time you go look at the bird is going to chirp like a bird does. Or you can search for things which are hidden away and so on. So you kind of imagine the types of interactions that become possible when you make the physical space become interactive. But also you can do a lot of measurements. Let's say you're in manufacturing. You can measure things and do a lot of things just using your phone. Well, then we started thinking about how can we make interfaces out of everyday objects. And what you see here is a very simple app where you have an object which doesn't have life or no electronics in it. And then you're saying, well, I want to put a fast forward button here. I want to put a stop button here. Maybe I want a dial here. Maybe I want a slider bar here. And these don't exist. So you're just dragging and dropping them on it and sort of designing your interface on a regular object, right? And all we needed to do now was to make this object come alive, and so that's the object, right? So now we want this object or anything around you to become your controller. Question is, how can we do that? And partly, of course, I already showed you some things that we can compute touch interactions in and around your phone and in that zone. But basically, if you have a magnet and we have our new thing, which I'll show you in a minute, you can find its position and orientation with respect to the magnet as well, right? So then any object can become your controller. So now what we did was we just took the ideas that we had in the space of figuring out how that pen was found in space, and we just made this object become interactive. So you'll see that in a minute. So this is just a design interface which shows how you want to customize your interface. And you just tell the interface, this is where you're going to put your magnet, and you're all done now. So the idea here is that you design your interface, customize it, embed it into everyday objects. So basically, you could take any object, right? Like mug or phone or shoes, all these inanimate objects, and say, hey, I want my push buttons here, I want my sliders here, and then put a magnet on the object, and then it'll become interactive. So we're going to see how that is done. So basically, the idea here is that we had to solve these magnetic field equations real time to determine the position and orientation of something which is in space around this magnet with respect to the magnet. And well, this is the only equation I'm going to show you here, but basically the field here and the magnet location, right? So this has to be done interactively. And you can kind of see that here. The tablet there is just for demo purposes, but basically you can see the position and orientation of this ring on your hand. And this is a prototype ring, right? So if, as I told you, like if we really put some effort and funds into making this small, it could just be a small thing sitting on your nail, for instance, right? So we can do that now. So we can get our discrete input buttons, gestures, tilts, proximity, and all the other continuous inputs put on your inanimate object, and you want that to be your controller. You just make a sticker out of it, put a magnet behind, and it becomes your controller. And here are some examples of what you can do with that. So you can kind of see is controlling TV and other things just with a sticker, right? That's all it takes, and you can see the control buttons on it. or you can have wearable controllers to control other things. Okay, so I'm going to move on to my last part of the talk. So here, we're going to talk about making the hands your user interface. So, well, what does this involve? So the idea here is, well, you're interacting with tablets, right, and screens. We want to move and get rid of the tablet. Instead, put it on your hands. And so your hands are your user interface. So I'll show you a little bit of what we have been doing here. This is one of our lab's projects, which
poses of a human hand using a deep learning algorithm. Depth sensing cameras enable a computer to process the different poses of a human hand. With these new deep learning algorithms, the computer recognizes and recreates the shape just as easily as our human brain does. This has the potential to change the way we interact with computers and the things around us. The deep learning model sees different portions of the hand, such as the palm or the fingers, and then figures out how they all work together, which is similar to the way the human brain works. Considering the self-occlusion and self-similarity of the hand, even portions of the hand that are not visible to the sensor can also be reconstructed by the deep learning algorithm.
Okay, so kind of have a feel for that. I'm not going to get into details of that. This is not the focus of the talk, but basically, deep learning has become one of the most important parts of growing computing infrastructure. You might have seen Siri and Amazon's Echo. A lot of these use these types of ideas from deep learning. And the important thing here is these new algorithms are smart. They can learn feature hierarchies, from speech to text to images to 3D vision. So, and it's also very significantly different from our past era, which was based on machine learning, where we had to encode and craft specific features for making these kinds of things happen. And this is very laborious and so on. But now the model itself is being learned by these deep learning ideas. So it creates entirely new ways of how we can think about computing. So as I said, I'm not going to have time to get into details, but building these architectures to work in real time is extremely challenging area. And a lot of our PhD students, the one that most recently graduated, he's now at MIT. He's one of the key contributors here, along with another student. So I'm kind of ending my talk here. So what I wanted to emphasize was making computers different from what they are today, making them intuitive, and making the interactions with them more easier and natural is opening up an entirely new world. And also, I think another important concept or idea that I try to communicate with you is the new user interface is not the computer. Actually, the new user interface are people like you. It's us. We are becoming the interface to the computer. And we see very, very important developments in many, many, many different areas following this type of developments in this area. And kind of think about it, right? If you think about it, even when we built cars, it created entirely new infrastructures, roads, and everything around, changed the way in which cities work and so on. So kind of think about the impact that the next generation emerging interfaces are going to have in terms of how we can extend the power of ourselves, which is kind of caged in because of very, very hard to use things like robotics, or hard to do things like designing and making things and so on. So what happens if we build machines that anybody can use, right? You can pretty much change the way competition today works. What happens if you and I can use machine tools that are extremely hard to use, make it easy, right? We don't have to send anything to China, and we'll become very competitive back here again. So those are the kinds of things that we are working in our labs. And now I'm going to switch to the Zyro demo, and as that comes, one of our students is going to set up a pottery demo where he's going to take everyday objects and a hand and make pots on the screen. So you're up, yeah. Dio and Torun.
I'm back with Zoe here and also our rover. As we were mentioning, both of these robots, they were built using the same modules, exactly the same pieces. You just basically can take it apart and convert them into anything you want. So one thing that I wanted to talk to you about, focusing more on this robotics kit, Zyro, is that I wanted to mention like 5 things that kind of define this technology that we have here. One of them, if I show you guys, while you guys are seeing this, what is the first thing that you guys notice? What is the first thing that catches your eye? What would that be? Maybe hands, maybe my hands, the way that I'm talking to you, the way that I'm using just my hands, seamless my hands to control it. So the coolest thing about this robot is that we can use just your hands gestures to control it. Hand gestures are just something intuitive. It's something, your hand is something that you had with you since you were born. And so it's not something that you really need to think about it whenever you want to control it. You just do it. So for example, if I want to go forward, I don't need to think about how I go forward. Sorry. I don't need to think about it how I go forward. I just do it like an accelerator of a car. Just an accelerator pedal. I can go just a little bit, just very slow, or I can go faster, just like pressing the gas pedal on a car. And what else? All of these gestures, they're intuitive. Whenever I use also my fingers to control the arms. If I want to bring the arms up, I want to wave it, I can just use my fingers to that. So these are things that I don't need to keep looking at my hands. It's not something like a controller. For example, you just got this new video game, it's awesome, it's great, but you just have this controller that you've never seen before, and you have to learn how to use it, and then it's going to take maybe 2 or maybe 1 or 2 days, like playing the whole day for you, to finally figure out how to use it. With this is just your hand, so it's not something that you need to learn how to use it. Second thing. Sure. Yeah, this is the second thing I wanted to talk about. This is a robot that it consists of a couple of modules. So they are fully independent. They are completely, they communicate among themselves and also with the glove. So Tarun, can you shake it really quick? Okay, thank you. So whenever you do the shake gesture, it disconnects. As you can see, mine is stopped, his stopped as well. So I can just take this apart. You can keep controlling it. So they are fully independent. They have no wires connected among them. They can communicate with themselves and also with the glove without needing any wires or anything. So they are completely independent. They connect also, they can be connected to the web, since we have for the connection between, how do I communicate my glove to my modules? They can communicate through Wi-Fi, so they can also be connected to the web. I could be maybe here in the US, I could be controlling my robot. Maybe in London, my robot could be there taking pictures of the Big Ben for me. Maybe in India, it would be maybe in Goa getting some sun. You can do just whatever you want. Another point that I wanted to bring is that it's completely gender neutral. Robotics is not something that is exclusively for boys or exclusive for girls. Everybody loves robotics and everybody wants to make their own robot. So it's not everything about this robot. We wanted it to be completely gender neutral because this is the world we live in. Another thing, sorry. Then the last thing that I wanted to talk about is that you can use any material. We want to bring the crafting out of every person to be able to build this robot. For these, we just use a couple of wheels that they were laser cut. We literally use wood for this part, and this is a yoga mat that we cut at our lab just to make the wheels, just to make the tires to make it look cool. And it does look super cool, and it also has adds some friction to it, so it's pretty cool. You can make this robot, as I mentioned, this is an 4x4 off-road robot, so it can go over obstacles like this. So yes, now, since you can bring any kind of material from your house, you can just grab some pieces of cardboard, do some crafting, play with it, and use your hands instead of just playing with a computer. We want everybody to be able to make their own robots without having to know any electronics or any coding or anything. just grab your scissors, grab some pieces, maybe grab some toys that you don't use it anymore. Grab your Legos, because these, they also connect to Lego. This is the idea. They're just anything, use anything in your house, anything around you to build your own robot and do the things that you want. Everything just controlling using your hand gestures.
Thank
so
you.
Using absolutely no user interface, just your own body to control it.
Yeah, thank you very much.
Thank you very much.
So if you want to play with these robots, they're going to be at the Envision Center for maybe hanging there for the next 1 hour if you want to. I'm going to switch and we are going to do a very quick demo of here. Can we switch to the screen? Okay. Okay. So Cecil is actually showing you a new type of controller using his hand. He's going to make parts on the screen, and the color is gone. It's not showing in color. Yeah, it's can we? Yeah, the color is changing. Okay. Yeah. So he's sort of moving his hand in space. So also I wanted to mention that almost everything you saw, all the code, everything was done in our labs. Our lab is sort of a mixture between certain parts of computer science and the ECE, like algorithms, but also geometry and computer vision. But we're also mechanical engineers, so we don't see the difference between some of these different worlds as it exists in academia. But also, like what Cecil is actually doing, which we don't see on the screen yet.
I'll put it up. Give me 1 second.
Okay, thanks. Yeah, we're just having some technical problems in the back. Okay, there you go. So he's got a pot, and his hand, actually, if you want to try it, he's not wearing anything. So he's kind of moving. This is one of the apps that we built very, very long time ago. At the beginning of these spatial controllers, there was a company called Leap that came to us and wanted us to do some cool stuff with the hand. So he's moving his hand, and the hand is detected in the spatial zone above the pot. But he's also pulling these tools and using these tools as carving metaphors and so on, which we all know how to do. But once you're done with this, literally in one of our demos in 2012, we actually showed in the CES show that you can just pick this part up, and your upload for printing is just take your hands and drop the part on the printer. It'll print the part. So we have been sort of playing with these ideas of tools and so on. Here all the tools are virtual. But there's also, if you sort of come to our labs and you want to play more, you can take any physical object and start carving out things on these pottery-like objects. He's kind of coloring that. So there are a lot of new metaphors that we have developed here. That's like a color bucket and so on. So with that, I think I want to move on and let's acknowledge. I wanted to acknowledge my students and postdocs and everyone else that has worked with us. And go to the next screen. Can we get back on the slides, please? Thanks. Thank you. Yeah. All right. So yeah. So he's back, and his tech demo. Oh well. Yeah. We're right there. So yeah, I wanted to acknowledge our whole team. A lot of this is team effort between multiple students and postdocs and undergrads and so on. So we form teams across different areas. And if you want to work in our lab, if you have gotten interested and excited, you're welcome to come and visit our labs. We also have a very nice toy museum in Gatewood building. It's a toy design class that me and my colleague were teaching, which I teach with my postdoc these days. And that's also open to the public. And in Gatewood, if you kind of peer through the windows, you'll find thousands of toys designed by, well, not thousands, maybe a few hundred of them, designed by our students. And I'll be happy to tour you and show you what we are up to in ME. So thank you very much.